Hello guys, so this is my third lecture on implementation of Ebbinghaus techniques for revision. So in this class we will discuss more concept or more things which I already learned yesterday. Let's see. So first of all, what do you mean by viscosity? So viscosity is nothing but resistance to flow. That means if there is some flow, if there will occur some resistance, that is made, that means that is known as viscosity of fluid. Okay, so if we compare water and honey, so in between this, honey is more viscous than water. That means viscosity of honey is more than water. And so I told you viscosity resistance to flow. That means for flow something, that means for flowing of any liquid, we have to give more certain amount of force so it can flow. That means viscosity will be less. That means resistance to flow is viscosity. That means opposite is what we have to give force so that the resistance will be less. No, resistance will be not less. That means we have to overcome that resistance. That is, for that we have to give more force. Okay, let's see. Now we are talking about region of viscosity. Two regions I will tell, and for one is liquid and another one is gas. For liquid, molecular cohesive forces. Okay, molecular cohesive forces is the region behind viscosity for liquid. So let's see, what do you mean by molecular cohesive forces? How? Let's see. Let's see. There is a surface. So if there is some molecules, okay, you can see there is some molecules. Okay, if this molecule wants to move in this direction, but due to molecular cohesive forces, these molecules will attract this molecule will attract this molecule attract this molecule attract this. Due to this, if it will move, if you want to move in this side, this molecule, so by default these whole molecules will be tends to move in that direction. So due to this, that molecule feels some resistance, so this reason for the viscosity happens. For this reason viscosity happens in liquid. Then for gas, so gas, but what is the region viscosity in gas? Molecular momentum transfer. Understood? Molecular momentum transfer. That means in gas there is many molecules are there, so they are moving in either direction, that means random direction, random motion. Due to these, resistances happen. If there is a flow or organized motion will be there, in that situation the resistance will be less. As there is many molecules are randomly moving, that means collide with each other always, so they cannot move freely or organized manner. So that time viscosity of gases happen. And so just listen one thing. There are two types of motions are there: random motion or organized motion, flow or organized motion. That means resistance to flow I already do. So flow. So if there is flow of gas, then organized motion will happen. But the thing is, in gas there is random motion, so viscosity of gas also there. And then we are discussing now main thing is Newton's law of viscosity. For this we have to be understand, before we enter concept of Newton's law of viscosity, we have to understand two things. One is no slip condition, then another thing is velocity profile. Okay, so in no slip condition, what do you mean by no slip condition? Okay, for no slip condition I want to show something. Okay, let's see. Let's see, this is a plate. Okay, this is a surface, solid surface. So when water is moving above that, so the molecules which is just attached to this surface, that they seems like stick with that surface. So there is no slip condition. It is the main concept. That means that when these water molecules are passing through above this surface, when the molecules are passing near this surface, very close to surface or just touch the surface, they seems like stick with each other. It is also experimental, remember. So there is, as it will stick with each other, that means it stick with this surface. So it seems like it is no slip condition. Okay, so the fluid in direct contact, in direct contact with solid surface will stick to the solid surface, and there is no relative motion between fluid and surface. So there is motion, but there is no relative motion. Relative motion is very keyword, you have to read. There is no any type of relative motion in between molecule and this surface. Okay, it is based on experimental observation. Next thing, main thing, remember, it always think of relative motion. In this what I am explaining, no slip condition, or you can say velocity profile, all this, remember, it is relative motion, because one plate is there and one is moving or two is moving. That means relative to each other, what will happen, what is its velocity. But every time it will move, but it is stick, it is moving. So this thing when happens, that time we have to be discuss on the relative motion. And the relative motion concept I will be explained when I will read the theory of motion chapter. Okay, for that time I will explain very clearly about relative motion and other thing. Okay, just listen. The fluid in direct contact with solid surface will stick to the solid surface, and there is no relative motion between fluid and surface, and it is based on experimental observation, not theoretical. It is experimental observation. Okay, then if another condition will happen, if there is if it is you can say it is a surface. Okay, some water molecule also stick with each other, but this plate also moving and water molecules are moving. That means there is a relative motion. When there is a relative motion 0, that means there is no slip condition will occur. Okay, then velocity profile. What do you mean by velocity profile? So in velocity profile, the the diagram will be, or the profile will be increasing. That means let's see, there is the surface. So in this surface many water molecules are going in this direction, but when the water molecule are touched with this surface, they are stick with each other, but these stick with each other, and that layers, upper layer, will also moving. But due to this restriction of motion of this molecule level, that upper level also get some impact or get some restriction of that below molecule layer. So that upper layer also feels some resistance. Due to this, their velocity also will be decreased before what is already moving with velocity. That means the velocity which is already moving, that will be less when it touch with that molecule level, and this will happen in increasing order. That means that upper level will restrict that upper level is restricted by that below level molecule levels, so that will happen. But if you make a profile, you can see this is a molecule level, and this is also a molecule level, this is also a molecule level, this is also a molecule level. So if you see, then you can see this point will, the starting of point is this, and if you going upside, you will find that the flow will be like that. That one I want to show that. Let's see. Okay, let's see, it is a, okay, so it is a molecule level. Okay, so okay, let's see. So this layer is stick with each other, so there is no any type of relative motion is there. But this upper layer will have more velocity than this below layer. But the one thing is, it is less velocity than it going before this restriction. There obviously there is some restriction, due to that their velocity must be decreased. But the thing is, if we go from lower to high, the lower will be very low, then the upper level will be just somewhat higher velocity, like that it will go. Okay, and what extent it will go, we will see in boundary layer theory. Okay, detail will be read in boundary layer theory. Just I will inform you that kind of thing are happening. Okay, so if we will see that in this diagram, I am doing a parabolic profile. Okay, which you can say 2y minus 2y square. Sorry, 2y minus y square. It can be of any type, but there just take a example, consider a parabolic. Okay, all the real fluids follows no slip mode. Yeah, all the real fluids follows no slip condition. Remember, all the real fluid. There is some ideal fluid. There is different type of fluids are there. We will discuss later. But one thing remember, all the real fluid. That means what we know, that type of fluid follows no slip condition. There is that don't type of any type of no slip condition. That means always there is some restriction will be must be there. That means there will be some profile we will get definitely. And remember, always we will not get this type of profile. It is maybe vary. Okay, just for example, I explain in this situation that it gives a parabolic profile, but profile may be different. Okay, that we will see later classes. Okay, remember two things is there. One is cohesive forces, another is adhesion force. Cohesion and adhesion, two things are there. Cohesion means attractive forces between two molecules of same nature. That means there is molecule of liquid and another is molecule of liquid. So due to the same molecule, that means due to the same condition, that means liquid, there is between them a cohesive forces. But you can another thing, that is adhesion. Adhesion is attraction force between two molecules of different nature. That means there is a molecule, there is a solid. So there will be some attraction between solid and liquid. There is known as adhesion. Okay. Then if I am just explaining and I am reading, so just listen. Okay. So there is a profile we will get by giving direction of increasing order of velocity from the no slip condition to the higher level. So if I will take some small element between that y direction, small element dy, if you will observe, that one thing will happen. Let's see this is a molecule in this section and another molecule is in this. If there is same velocity, then it will move in this direction same parallelly. That means it will move parallelly, it will also move parallelly. But if this velocity, this molecule's velocity is high than this, then it will move like this. Okay, it will move like this. That means its velocity is more than it. So this condition I am now observing. Okay. So before, if it is parallel, then AB and U it is, and U plus du. That means it is more velocity than lower level. So if I will doing this thing, this direction, then I will get a angle which is d theta, and this will be dy, I already mentioned, and this will be du into dt. That means this direction u will be what? With no distance, we know velocity is what? Meter per second. That means distance per time. So I want to distance du I can write du into dt, which is velocity du. Okay, which is du, it is distance. Okay, so this thing happened. So tan d theta is equal to du into dt by dy. Okay, that means tan thing d theta. Okay, d theta is very small angle, so we can neglect tan. So d theta is equal to du into dy. So velocity gradient in the transverse direction du by dy. So for arranging this equation, I am getting that d theta by dt is equal to du by dy. Okay, d theta by dt is equal to the rate of angular deformation or rate of shear strain. So d theta, but the angle change with respect to time is known as rate of angular deformation. Okay, I know rate of deformation or rate of shear strain. I already know d alpha by dt, but here d theta by dt, another angle d theta is included. So d theta by dt is equal to rate of angular deformation. So same thing, angular deformation, that means rate of shear strain, which already I studied before classes. So that means previous classes. So in this rate of shear strain, so rate of shear strain is this thing. Also that time I have mentioned alpha, and this time I am mentioning theta. Okay, and remember d theta by dt is equal to du by dy, du by dy, du by dy. Okay, so let's see. Then As per Newton's law of viscosity, shear stress is directly proportional to shear strain. Newton, that now I am discussing about Newton's law of viscosity. So, as per Newton's law of viscosity, shear stress is directly proportional to rate of shear strain. Remember, as per Newton's law of viscosity, shear stress, shear stress is directly proportional to shear strain. Rate of shear strain, not shear strain, rate of shear strain, angle से. Shear stress is directly proportional to shear strain. That means I can say shear stress is tau, directly proportional to shear strain, but that means d theta by dt. So tau is equal to, as proportionality, so proportionality constant will be there, though there is mu. So tau is equal to mu d theta by dt. Okay, and dt I can write dt as dy. So I can write tau is directly proportional to d theta by dt, and I know d theta by dt is equal to du by dy. So I can write tau is equal to mu du by dy. It should be remembered. Every time you ask in exam and every problem you have to be implement this formula to get the answer. So I already said that tau is equal to mu du by dy. So now what do you mean by mu? Mu what is? Coefficient of viscosity, or you can say dynamic viscosity. Okay, coefficient of viscosity, we can say dynamic viscosity. Okay, so mu we can define just balancing this equation. So I can say mu is equal to tau by du by dy, and we know that tau is equal to Pascal, that is pressure, that means stress, shear stress already the unit is Pascal. So Pascal by 1 by second. Okay, there is velocity by time, so you can say velocity is meter per second and divided by second, meter per second and divided by distance, meter. Okay, so meter will cancel 1 by second. Okay, so mu, that means will be Pascal into second. Okay, so mu, what is viscosity? That means coefficient of viscosity is mu is Pascal into second. Okay, tau what is shear stress. Okay, mu what is dynamic viscosity or coefficient of viscosity. It is dynamic viscosity, remember. Then if you ask me what is the unit, I already explained that the unit of dynamic viscosity, that means mu is Pascal second. Okay, and it is in SI unit. Okay, in case unit you can write Pascal is Newton per meter square second. Okay, second is same every system, second is second, that means time always referred as second. So in MK system, Pascal is Newton per meter square and time is second. So in SI unit Pascal second, in MKS unit Newton per meter square second. Remember that. So sorry, I have to be no. That means in case unit I have to be changed. That means what is the actual thing. So yeah, in case system I write that Pascal thing into Newton per meter square second. So if I explore that, then I can see that Newton per meter square. So Newton is what? Mass into acceleration. So mass into acceleration in meter per second. So like that I can get kg into meter per second square divided by 1 by meter square. So meter square will cancel, we will get, and second will also cancel, so we will get kg per meter second. Kg per meter, that means we will get mass as its unit. Okay, so kg per meter second is the unit of kg per meter second. Kg per meter second is the unit of dynamic viscosity, or you can say in MKS system. Okay, in MKS system, kg per meter second, that means Pascal into second you can say, or you can, by solving or exploring into depth, you will get kg per meter second. Okay, finally then CGS units come. So CGS units, it will be obviously that is kg per meter second, it will in CGS system gram per centimeter second. If we exploring that, we will get 1 poise is equal to 1 gram per cm square, cm second. 1 poise is equal to 1 gram per centimeter second. So 1 poise, if I will convert in the MK system, so we will get 1 poise is equal to 10 to the power minus 3 divided by 10 to the power minus 2 kg per meter second. So 1 poise is equal to 0.1 kg per meter second. Okay, so 1 poise is equal to, so by this explanation, just one two thing you have to remember. So what is the unit of dynamic viscosity? Mu is equal to Pascal second. If we see in case system, you will get kg per meter second, and in CGS unit 1 poise is equal to, in CGS system it will be 1 gram per centimeter second, but if we convert into 1 poise, so 1 poise is equal to 0.1 kg per meter second. So it is a relation between poise and kg per meter second. Okay, 1 poise is equal to 0. kg per meter. So very 1 poise is very small unit. Okay, then another thing, kinematic viscosity. So we will learn now kinematic viscosity. So kinematic viscosity is denoted as nu. So nu is mu by rho, that means mu by density, that means dynamic viscosity by density. Dynamic, so if we will solve through its unit, so you will get dynamic viscosity's unit is kg per meter second, and divided by rho, that means mass per volume, that means kg per meter cube. So if you bring and multiply with these two units, so you will get kg per meter second into kg per meter second into meter cube per kg. So meter will be cancelled, that third power, it will get second power of meter. kg will be cancelled, you will get meter square per second. So the unit of kinematic viscosity is meter square per second. It is very important things for any type of examination. Meter square per second. Okay, it is both for meter square is second is both for MK system as well as SI system. Okay, remember that, and it will be very important. If we will CGS system, that in dynamic viscosity in CGS system 1 poison 0.1 kg per meter second, but in kinematic viscosity, as we know, the unit is meter square per second. So if we convert it into CGS system, you will get 1 Stoke. That means in this kinematic viscosity we are concerning about Stoke. 1 Stoke is equal to 10 to the power minus 4. That means 0.0001 meter square per second. Okay, that should be very very important. That means 10 to the power minus 4 meter square per second. But if you will see, 1 poise is equal to 0.1 kg per meter second. 1 Stoke is equal to 10 to the power minus meter square per second. That means in this is kinematic viscosity. Okay. So now we are concerning that what do you mean by mu? Actually, the significance of mu, or you can say, I want to explain you what is the difference between dynamic viscosity and kinematic viscosity. Just look that in dynamic viscosity I have got which unit? Kg per meter square. That means that is mass is present. So we need another system which without mass. So we will get that without mass also a formula or a unit also there for viscosity. So it is kinematic viscosity, and this unit is meter square per second. Meter square per second. That means we are not bothering about mass. Okay, that means we are just focusing about meter and second. Okay, speed. Kinematic, that means some motion, so we are concentrating just about motion. But dynamic viscosity is mass is should be there for any type of calculation. Okay, so for dynamic viscosity it is mass related, and kinematic viscosity is motion related. It should be very very clear. Then what is the reason behind kinematic viscosity? So reason not, but I want to say something that larger the kinematic viscosity, momentum diffusivity will be more. Understood or not? You understood or not? So higher the value of kinematic viscosity mu, higher will be momentum diffusivity. Okay. So what do you mean by momentum diffusivity? So just I am going to explain for real life exam. So just correlated is not direct thing, but just correlated thing. There is many cycle in a stack, and which is closely packed with each other. So I just push one cycle, that will leads to pushing another cycle in front of that cycle. So like that it will goes on. So what I just do, I just do one thing, one push, and it will goes on goal. So like that, if you can see, if there is molecule, one layer, it is going in this direction, but stick due to this solid surface, due to this restriction, that upper layer will be also restriction. That means that velocity will be decreased. That upper layer also feel some restriction, that also decrease. So like that it is goes on. These, that means the higher the velocity, that means higher the kinematic velocity, the momentum diffusivity, that means it is like that, it will go on increasing. Then it is so this thing, that means the momentum diffusivity, that means momentum is diffused. So it is diffused large distance. Then higher the kinematic viscosity, large will be the momentum diffusivity. And another case will be also there, if that cycles instant will be placed some distantly, so less number of cycle will be collapsed or cell will fail. So there is difference on the how the things are closely packed. If the things are not closely packed, then kinematic viscosity will be less. So then diffusivity will be certain. That means restriction upper level, restriction will be upper level. That will not go very high. And remember this thing, how distance will be go momentum diffusivity. It also in boundary layer theory, that at that time we will explain very deep manner. Okay, just one thing, no, higher the value of kinematic viscosity, higher will be the momentum diffusivity. It is should be remember. Okay, so once again I am repeating that 1 poise is equal to 0.1 kg per meter second, and 1 stroke is equal to 10 to the power minus 4 meter square per second. Okay, so as I have just discussed that kinematic viscosity, just remember kinematic viscosity is viscosity, but if you compare with dynamic viscosity and kinematic viscosity, just the unit difference. That means in unit there is mass is there, but in this just meter is there is no mass. So just think like in viscosity. So kinematic viscosity, that means viscosity, that means restriction will be, if restriction will be more, that means closely packed. If closely packed, that means restriction more. So this will, if restriction is more, then viscosity will be more, then will be lead to many type of layer. That means it will increasing momentum diffusivity in higher level. That means it will restrict this thing, this layer, it will restrict 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 this layer, it will go increasing. But this, how distance it will go, we will see in which boundary layer theory. For that of sake, just wait. Okay, I think you will clear. So now we are going Newton's law of viscosity, which I already said that shear stress is directly on shear strength. So now we are just explaining further on this topic. Okay, or you can say the only I am doing some formula. So tau is equal to, which is shear stress, is directly proportional to rate of shear stress. So you can say tau is equal to mu into du by dy. Then u is equal to u is a function of y. That means y vary. Then how y vary? U velocity profile will be vary. Okay. That means how the velocity will be vary, that according to that velocity profile will vary. Okay, now I am going to one thing, that linearization of Newton's law of viscosity. Linearization, where we are doing some linear thing to this Newton's law of viscosity, to explain or understood very easily by some mathematical model. Okay, if there is let's see, there is some layer. I am doing a plate also in this, here one plate and here also one plate. When I am doing that, it will goes on, velocity will increase. At this is maximum, it is v. Okay, and this is y direction, that means this I told you y. Okay, and okay, as I already said that it is linearization of Newton's law of viscosity. So I can draw a straight line from this to this. It is linear. Okay, so this error, this is the profile, but we are just doing some linear manner. We draw a straight line for our understanding and for our simplification of math. So just draw a straight line. So due to this, but I am doing this, so that point is error. That means this distance is error. So what I am done that, remember, error will be minimized when height, that means this is y, this is y direction, not y. This height, it is h, it is not y actually, it is h. This height, how much will be less, then the error will be less. Okay, then okay, y is equal to 0, that means starting point, it is starting point, y is equal to 0, u is equal to also 0, here u also 0 and y also here 0, in this point, particular touching point. Okay, if we go increasing, it is the highest point. So here y is equal to h, so y also total distance, y direction. Okay, so in this direction h is a distance, which is height is maximum in this diagram. So in this diagram h, so h, y is equal to h, and here u is equal to b. Remember, I already said that it is here u is equal to b, maximum velocity, and it is no slip condition. Okay, that means there is some stick on these two plate. Okay, there is some stick on this two plate. Okay, so I am just reading. If h is small, we can assume linear velocity profile. If h is small, we can assume linear velocity profile. Velocity profile will be linear, not linear. Velocity profile will be linear. Obviously, we know in math, but if you are not understanding, we will explain in math. Okay. So as it is linear velocity profile, we know the straight line formula is y is equal to a plus cx. Okay, so we can write u is equal to a plus by, where a and b are arbitrary constants. Okay, and also b is also here slope. Okay, so u is equal to a plus by. So at as it is straight line equation, so at y is equal to 0, u is equal to also 0. So I can write u as 0, and is equal to a plus b, and y is 0. Okay, so just putting that thing, and I will get a is equal to 0. That means first a is equal to 0. Then at second, two boundary. So at y is equal to h, u is equal to v. So we know b is equal to will be, so b will be 0 plus b whole h. So we will get b is equal to b by h. Okay, as u is equal to b, we know a plus by. So here there is u is equal to v, so v is equal to a plus, we already know a is equal to 0, so b, h is y is equal to h, so b is equal to v by h. So we will get u is equal to u is equal to by divided by h, which is linear velocity profile, v into y by h. How v into y by h? As u is equal to v plus vy, so u is equal to a is 0, so it will remove, so b is equal to v by h, and y, so y, okay, v by h into y, or you can say y into, sorry, v into y by h, okay, v into y by h. So I can write tau shear stress is equal to mu du by dy. So replacing u with v into y by h, we will get tau is equal to mu, we know tau is equal to mu du by dy, so it will be mu d by dy, then derivative will be there, v into y by h. So we will get tau is equal to mu v divided by, okay, mu v divided by, so yeah, so u is equal to v to include it, okay, I got it, yeah. So vy by h, so tau is equal to mu v by h, okay, shear stress. So tau I can write mu, that means dynamic viscosity, to v by h if I linearization of, yeah. And remember, this shear stress formula is independent of y here, but before formula we know that y should be there, so in linearization there is independent of y, okay. I remember, so from this linearization Newton's law of viscosity, we will get tau is equal to mu v by h. So you can say tau is inversely proportional to 1 by h, and tau is directly proportional to dynamic viscosity, that means mu, tau is directly mu, and tau is directly proportional to v. It should be remembered, it is very, very important. So if I will draw two plate and line, so you will get tau is throughout same, as tau is throughout same in shear stress variation, okay, and in velocity variation it is linear. Before that we will proceed for new concept. I want to show some thing which I already get, that tau is direct inversely proportional to height, that means the height will be less, the shear stress will be more, or you can say the height will be less, the shear stress will be less, but constant throughout, but how shear stress is varying, that means is less or more, it is depend on height. If height is more, shear stress is less. If height is less, then shear stress is more, but other thing is same. That means we know that tau is equal to mu v by h, so obviously that, and mu v by h, then you can say if that means shear stress will be increased, that means if velocity will increase, then shear stress also will increase. if dynamic viscosity means kg per meter second, that means viscosity if will increase, then shear stress will increase, or shear stress will increase viscosity, it's same thing. Okay, so next thing we will going last topic for this video is calculation of drag force. Okay, but calculation of drag force, what do you mean by drag force? We have to first focus. So what do you mean by drag force? Let's think. There is two people are going. There are two people are going. So between them, if they are going, so now we are going to understand. So what do you mean actually drag? So let's visualize with some real life example. So let's see, two people are running. One is greater speed than another. Okay. So when they are moving or they are running, you will observe that, or you will investigate and observe that. You can observe that the man who is going more speed will pull by that slower speed. That means that higher speed man will observe a force in backward direction, that in opposite direction. That is actually drag force. And another thing we have to be remember that slower speed will also want to, and or you can say that lower speed man also get force to move fast by that faster man. Okay, so you will see that by example in real life. So now I am going to see in how it will happening in practical or in fluid. So let's see just once. Okay, let's see, this is water level between two plates. So as if this plate will move and water is also moving direction, but the speed of this plate is more than this water, so this plate will feel, or you can say, yeah, will impact by this slower one, so it will feel some force in backward direction due to the slower speed of this water level rather than the speed of this plate. So due to this, some force will, I already said, some force will implemented in backward direction. That backward direction, that opposite direction force is known as drag force in water or in any type of fluid. Remember, it is very, very key thing. So it is the basic fundamental, and then you can say drag force is tau area, and you can write as tau into area. So you can write tau is mu v by h. So you can write drag force is mu v by h into a. Okay, and remember tau it is here, it is shear stress must be uniformly over entire area A.
total entire area A, that flat area A, shear stress must be uniform, that every point the shear stress is must, that means every point in this plate is shear stress is be equal, uniform, equal. Okay, if not uniform, if not equal over entire area, that is a plate, that means plate like this. So if not uniform entire area A, then we have to do some integration. After that we will get that actual area. If but we are considering that it is uniform throughout the area, that shear stress. Okay, and A is area, that area, that plate area. Okay, if not, I already said that if not uniform over entire area A, then if I derive or derivative or apply differential equation or applying derivative here, so dfd is equal to tau into dA. So fd will be integration tau dA. Okay, so remember tau is equal to, so if not uniform over entire area A, then what happens? If not uniform over entire area A, then dfd will be tau dA. That means we have to integrate over the area, whole area we have to integrate, as there is different thing, there is different area. So if there is not uniform, we have to do integration, obviously that. So d will be integration tau d. Remember, if it is uniform tau A, if it is not uniform, integration tau A. And remember tau is equal to mu v by h. Okay, bye, see you, and stay safe and secure your life, and please share and subscribe this channel and like please. And please, my recommendation is please watch these videos in 1.25x speed or 1.50x speed as per your wish. Okay, bye, see you in next video.